All right, we're going to conclude section 14.5 in this video. We'll continue it on page 943. And we're going to do number 20, which says in exercises 19 through 31, find the volume V of the region. And 20 says the solid region bounded above by the sphere x squared plus y squared plus z squared equals 2, and below by the circular paraboloid z equals x squared plus y squared. All right, so for our bounds, our top was we were bounded above by the sphere. So that circular parabola they gave us, z equals x squared plus y squared, that's a parabola that opens up from the origin. So we know that everything we're working with here is positive. So the top part of this region is going to be the positive part of the sphere. So z equals the square root of 2 minus x squared minus y squared. We'll go ahead and convert that to cylindrical coordinates, which is 2 minus r squared. And that's our F1. Sorry, I keep forgetting to write that there. So that's going to be our F1 as the top. And then our bottom is the paraboloid, which was z equals x squared plus y squared, or z equals r squared. And then our sides. So when they don't give us any sides, we know for sure we have to intersect the top and the bottom. I tend to do it all the time because you never can really, you can if you visualize the picture, decipher whether you need to intersect the top and the bottom. But sometimes even if they give you some sides, it seems like your textbook, if they give you explicitly and they say the sides are, then you don't need to intersect the top and the bottom. But I haven't done every single problem in the textbook, so I don't want to say that for certain. But when they don't give you what the sides are, you know you have to intersect the top and the bottom for sure. So intersection of top and bottom. So you can do it in cylindrical coordinates, or you can do it in rectangular coordinates. If I do it in cylindrical coordinates, all I'm going to do is set r squared equal to the square root of 2 minus r squared. So I'm just setting these z's equal to one another. But when I do that, I'm going to square both sides, and I'm going to get a fourth degree polynomial. If I square both sides, if I set this equal to that and I square both sides, I'm going to get a second degree polynomial, which is easier to work with than a fourth degree polynomial. So I'm going to use these in rectangular versus using the cylindrical. But it doesn't matter. You're going to get the same answer regardless. So substitute. And up here, I'm not going to set them equal to one another. I can, and I will get the same answer that way, but it's just going to make my life more difficult. I want one variable. So what I'm going to do is take x squared plus y squared, and I'm going to substitute this in and square both sides, but I'm going to end up getting everything back in terms of z in the end anyway. So if I substitute let's say substitute z squared, or z equals x squared plus y squared. We'll do it this way, into 2 equals, so the sphere that they gave us, which was actually 2 equals x squared plus y squared plus z squared. Equals x squared plus y squared plus z squared. Now, in doing that, I'm not using this exactly. So I want to keep in mind that this specifies that z is greater than or equal to 0. So when we go through this, we just need to keep that in mind. So let's write it right here. Because both of these, z is greater than or equal to 0, z is greater than or equal to 0 right there. So now when we take this and we put it in to here, we end up with x squared plus y squared, that's z. So we end up just with 2 equals z plus z squared, which is a quadratic. So we end up with z squared plus z minus 2 equals 0, which that factors into z plus 2 times z minus 1 equals 0, which tells us z equals negative 2 or z equals 1. But remember, z has to be greater than or equal to 0. So it's certainly not that. So that tells us z equals 1. Now, we're trying to get our sides. Z equals 1 is a height. That's not that wouldn't give us our sides. So we need this to be in terms of x and y because we want to look at this in the xy plane. But if you were to take this paraboloid and intersect it with that hemisphere, they would intersect at a height of z equals 1. But we want to know, what does that intersection look like if we take it and we project it down into the xy plane. So we're going to substitute z equals 1 into either one of those equations. It doesn't matter which one you substitute it into, but it's easier, of course, here. Z equals x squared plus y squared to get x squared plus y squared equals 1. So those are our sides, and we know that we've seen this over and over again, how to do that in polar coordinates. So I'm just going to jump to that without sketching it. So theta varies between 0 and 2 pi, and r varies between 0 and 1. So now we can go ahead and set up our iterated integral. And for sake of time, I'm not going to write down what d is because I want to see if I can squeeze in one more example before our time runs out. So 0 to 2 pi for our theta, 0 to 1 for our r, and z goes from, our bottom was r squared, our top was the square root of 2 minus r squared. Now we were asked for a volume of this region, so our integrand is 1, but then don't forget about times that r, and then these are z's, dz, dr, d theta. All right, so I want to try to at least start one more problem. So let's look at number 26. I want to give you all a good mix of problems. So 26, same directions as 20, but now the region we're finding the volume of is the solid region bounded above by the cone z equals 8 minus the square root of x squared plus y squared. So bounds top, where top is your f2, z equals 8 minus the square root of x squared plus y squared. And we'll go ahead and convert that now. That's z equals 8 minus r. The bottom, which is our f1, was something, the xy plane, so z equals 0. All right, and then the sides, the cylinder x squared plus y squared equals 2x, and below by the xy plane. So here we're going to act under the assumption that they just gave us the sides, that we don't need to intersect the top and the bottom. So if we did have to intersect the top and the bottom, we would get r equals 8 if we did that. And then you would just check and see, is that region outside of this region that they gave us for the sides already, which it will be, because the region they gave us for the sides is a cylinder that would be completely inside of, what did I say, r equals 8? Yeah, r equals 8, which would be a circle centered at the origin, but then you take that and you expand it up and down the z-axis, so that would be a cylinder as well. So this, if we were to intersect these, we would get a cylinder that's much bigger than the cylinder that they gave us. So we don't need to consider the intersection of that and that. So they gave us x squared plus y squared equals 2x, and we've done this a couple of times going through and seeing what this is if we were going to sketch it. But this time I'm not going to sketch it. I'm just going to jump to cylindrical coordinates. So this is r squared equals 2 times, remember x is r cosine theta. And move all this over to the left. R squared minus 2r cosine theta equals 0. If we factor out an r from both of these terms, we're going to end up with r equals 0 or r equals 2 cosine theta. Now we have to figure out what does theta vary between from this. Now if we had this picture, which we've seen a couple of times, but I'm going to make sure that we know how to do it without the picture. So remember, our r always needs to be greater than or equal to 0. So that has to be greater than or equal to 0, which says cosine of theta has to be greater than or equal to 0, which tells us that theta is going to have to vary between negative pi over 2. Sorry, so negative and pi over 2. So now we have our bounds. We have what theta varies between. We have what r varies between 0 and 2 cosine theta. And we have what z varies between 0 and 8 minus r. And now we can go ahead and set up our iterated integral. Sorry, I rushed through this one. I just want to make sure you got to see a good combination of the different types of algebra that we would encounter. So we're going to have the iterated integral. Theta goes from negative pi over 2 to pi over 2. R goes from 0 to 2 cosine theta. And z goes from 0 to 8 minus r. And then our integrand is 1 for volume, and then the r for cylindrical coordinates. These are z's, dz. Those are r's, dr. And those are thetas, d theta. All right, so that concludes section 14.5, and then we'll start section 14.6 in the next video.